It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappin' in? Today we're going to learn about a mass spectrometer and apply the first right-hand rule to a charge in a magnetic field. So we can use a mass spectrometer to measure the mass to charge ratio of positive ions as well as separate ions of different isotopes. So we say and separate isotopes. And all that is are ions of different number of neutrons. So to look at a mass spectrometer, what we're going to do is set up a set of parallel plates. Let's say that the right plate is positive and the left plate will be our negative plate. We're going to take a positive test charge, just a positive charge, and we're going to shoot it in between the two plates. Now our goal is for the positive charge to go straight down in between the two plates. But as we have it set up, we know that the positive charge is going to get deflected towards the negative plate or the left side. So right now, the only force we have acting on the positive charge is the electrostatic force, which is pushing it towards the left. As we know, it goes from the positive to the negative parallel plate. So we'll draw our electrostatic field lines. Our goal, again, is to have the positive charge travel straight down. So in order to do this, we must have a force that's counteracting the electrostatic force, and that's going to be the magnetic force. So we somehow need the magnetic force pushing the charge to the right. We'll call that F sub B. We're going to take the first right-hand rule to determine the direction of the magnetic field lines, the north and south poles, in order to get the positive charge to travel straight down. So we know our thumb represents the direction of the positive charge. The positive charge we want it going down, so our thumb is going to point straight down. The magnetic field, or the magnetic force, that's the direction our palm is pushing on the charge, and we want it to push the charge towards the positive plate, or towards the right. Sorry, I know mine is opposite than yours. Which means our fingers point in the direction of the magnetic field, and as we can see, our fingers are pointing into the page. So the magnetic field is going into the page, and we'll represent that with X's. Let's use blue. So that means that the North Pole is pointing into the wall. So what we can do is we can utilize Newton's second law, which says that A is equal to F net over the mass. we'll multiply both sides by the mass. So ma is equal to the net force. We want the object traveling at a constant velocity in between the two parallel plates. So ma will become 0. And the two forces acting on it are the electrostatic force, which is going to the left, and the magnetic force going to the right. So F sub B minus F sub E. Let's add F sub E to the other side. We're left with F sub B is equal to F sub E. Now if we want to calculate each one of these or break them down, we can look at formulas we developed earlier for the electric field strength and the magnetic field strength. We know that the electric field strength E is equal to F sub E over Q, which means F sub E is E times Q. And we know that the magnetic field strength is F sub B over Q times the velocity of the charge. So if we get F sub B by itself, we have F sub B is B Q V. From Newton's second law, we know these two equations are equal to each other. So we can write B times Q times V is equal to E times Q. If we get the velocity by itself, so we can solve for the velocity of the charged particle, we get V is equal to E times Q over B times Q. And notice the Q's cancel out, so the velocity of the charge, to get it to travel in a straight line, is equal to the electric field strength all over the magnetic field strength. So V is equal to E over B. If we scroll up back to our parallel plates, we can see that eventually the charge is going to leave the parallel plates. And what we can do is keep the magnetic field going into the page and observe what happens to the charge. So we know that the magnetic field is pushing the charge towards the right. So as we could see over time without the electric field, the charge is going to continue following a circular path. And what we could do is put plates on the other side of the magnetic field, or a wall, and measure where the charge hits those plates. So we're going to utilize Newton's second law again, but notice that the particle without the electric field is moving in a circle. So if we look at Newton's second law, F net equals ma, the net force acting on the charged particle is just the magnetic force, so F sub B, but since it's traveling in a circle, is equal to ma sub c, the centripetal acceleration. And we know F sub B is equal to QVB, or QVB, we'll say, is equal to M, and A sub C is equal to V squared over R. So what we can do is solve for the radius, the radius of the circle, the path that the charge takes. So we'll multiply both sides by R and divide by QVB. So we have R is equal to mv squared all over QVB. Notice one of the V's cancels out. So we're left with the radius of the path that the charge takes is m times v over q times b. As I said earlier, we could measure the mass to charge ratio. So if we want to get m over q by itself, we'll multiply both sides by b over v. So m over q, the mass to charge ratio, is equal to b, the magnetic field strength, times the radius, all over the velocity of the charge. So in this case, notice the things that we could control are the magnetic field strength. We could control the velocity of the charged particle, and by measuring its radius of the circle, we could find the mass to charge ratio. So why don't we do a practice problem together, and this is practice problem number 3. So, practice problem number 3. A charged particle enters the magnetic field of a mass spectrometer at a speed of 1.79 times 10 to the 6 meters per second. So V 1.79 times 10 to the 6 meters per second. It subsequently moves in a circular orbit with a radius of 16 centimeters, so R 0.16 meters, in a uniform magnetic field of magnitude 0.350 teslas. B 0.350 teslas. Having a direction perpendicular to the particle's velocity, therefore we don't need to take the sine theta. Find the mass to charge ratio. So we want to find M over Q. Let's start with the formula we have in your reference table, and that is R is equal to M times V over Q times B. So if we want to get M over Q by itself, multiply both sides by B times R, and divide by the velocity. So we get M over Q is equal to 0.350 teslas times the radius, 0.16 meters, all over the velocity of the particle, 1.79 times 10 to the 6 meters per second. Plug and chug, and we get a mass to charge ratio of 3.13 times 10 to the negative 8th kilograms per coulomb. And that's it for this video, so please like and subscribe if you found it useful. See ya!